Hello, happy Friday, everyone, and welcome to today's lecture recap. So I want to start with a little bit of a recap of what we did last time. So we talked about an interesting problem, a real-world sort of problem, where you have a system that's subject to various forces, and we want to find the mechanical equilibrium position, and we want to find what is the frequency of small oscillations around that equilibrium position. So our example had a piston and a cylinder, and there was a force from the gas below the piston. There's a force from the outside air pressure, and then there's a force of gravity. And so the general method that we want to employ is first to understand what is the net force on our object as a function of the position. In this case, the position that we care about is the height of the piston. And so we want to basically, for each of those forces in turn, figure out what is the expression for the force in terms of this height, and then write down an expression then for the net force. And this is what we came up with, 1,500 joules divided by h minus 5,000 newtons. And the first term had to do with the fact that as we compress the gas more and more, there's a larger and larger upward force. The second term was from the combination of gravity and the outside air pressure pushing down, and those things don't depend on the height, and so we get this constant term. If you plot this function as a function of the height, then that's a decreasing function of h, and it goes through 0 at some point, and then it goes negative. And that's what we expect for the situation when we have a restoring force. So if we have a displacement, if we have an h, which is in this case very small, we have a low piston, that means there's a big upward force. And then if we bring the piston up, there's a downward force. And so we see we have those restoring forces. So the first thing we want to understand is how do we find the equilibrium position? Excuse me. Okay. And so then that's just equal to, that's the place where the net force is going to be equal to 0. So we just take our expression here, set it to 0, and then we solve for h. So that is the equilibrium position. Then we want to figure out what is the frequency for small oscillations around the equilibrium position. And this is where we want to basically look at the slope of our function at that specific point where it crosses the axis. And so that's going to be the derivative of this net force as a function of position. So we take that derivative and then we evaluate it at the place where the function itself is equal to 0. And then that gives us the slope. Okay, it's going to be a negative slope. And then this quantity that we call k is basically the magnitude of that. Or in other words, k is minus f prime at h equilibrium. So this is the k that we then plug into our formula for the angular frequency. Omega equals the square root of k over m. And then if we want the regular frequency, we just divide that by 2 pi. So I just have one comment about this. In some problems, like in our tutorial problem this week, there's actually a spring involved. And the spring, it might have a particular spring constant k. And if that's the only thing that's exerting a force in the system, then the frequency is just going to be determined by plugging that k into this formula. But generally speaking, if you've got a spring and then other forces involved, and you want to figure out the oscillation frequency, then the k that you need to use is not the spring constant. It's the k that you get by doing this procedure. Okay, so it might be that one of the terms in this net force is minus kx from that spring, but you can have various other terms, and you have to include them all, and then go through this procedure of finding the equilibrium position, and then taking the derivative of our force at the equilibrium position. Okay, so have a look at the tutorial solutions for this week to see an example of that, and then there's another problem, the third problem in the homework is like that one. So now we're going to move on to talking about a different topic. It's still related to oscillations, but we want to think about oscillations from the point of view of energy. So we want to understand what kind of energy is relevant in a simple harmonic oscillator, or in simple harmonic motion. And it's interesting because you basically have this transfer of energy back and forth between two different varieties. Okay, so the most obvious kind of energy that we have when we have an oscillator is the kinetic energy. So you have a mass, it's got a velocity, and so you know that there's some energy there, which is half mv squared. But during the oscillation, the actual velocity changes with time, and so it can actually be zero at certain points in the oscillation, at the very bottom or the very top. And so that means that the kinetic energy that we have at some points in the oscillation, when it's moving, say, through the equilibrium position, that kinetic energy must be transferred somewhere else, because there's no kinetic energy at the extremum of the oscillation. So where does it go? So the other kind of energy that we have is some potential energy. And in the simple case of having an oscillation of a mass on a spring, you may have seen a formula for potential energy of a spring, which is that it's equal to 1/2 times k times delta x squared, where delta x is the displacement from equilibrium. And so in the oscillating spring system, we have half mv squared plus half k delta x squared. That thing sums up to the total energy, and that remains constant. But some of the time, the kinetic energy is a larger fraction of it. Some of the time, the potential energy is a larger fraction of it. One thing that I wanted to point out is that this formula for potential energy, you could actually use this in more general situations other than just having a simple spring. Okay, so basically any time when we have simple harmonic motion, even if there are other forces involved, like in our example of the air leg, you could still understand that there's some potential energy. It's given by the same formula, except that you use the k for the entire system, like we described in the previous slide. So let's actually I'm going to give a quick derivation of that, just to help you understand that. And also, just in general, where does this half kx squared formula come from if you were not familiar with it? So we'll think about a general oscillating system. I've drawn a spring system here, but it could be something else. And the thing that I want to start out by noticing is that there are these specific locations where the kinetic energy is maximized. Okay, those are the places where you have the largest velocity, and we know that that's the place where the mass goes through the equilibrium position. And so let's define, it's common to define our potential energy relative to that position. Okay, so let's imagine we're doing that. And in that case, we would say the potential energy for that configuration is 0. And then the total energy of the system is a half m times this maximum velocity squared. Okay, so this is one way to write the total energy of the system. It's half m times the v squared, where you take v to be the maximum velocity during the entire oscillation. So what we're going to do is just rewrite this. We're going to rewrite this expression for the total energy in a way that involves the amplitude of the oscillation rather than the maximum velocity. So in examples that we had in class last time, we understood that the maximum velocity during an oscillation was equal to the amplitude times omega, the angular frequency. And remember, the way to see that is to start with our a cos omega t plus phi formula for the motion of an oscillator, for the displacement. Take a derivative to find the velocity, and then you get minus a omega sine omega t plus phi. And so then looking at the number outside of the sine function, that was a omega, and so that determines basically the amplitude of the velocity fluctuations, of the velocity oscillations. Okay, and the maximum of that then is going to be a times omega. Okay, so we can start with this expression for the total energy, and then just replace the v by a times omega. And actually, I'll do one more step, which is to replace the omega by the square root of k over m. Okay. So we're going to plug this expression into this formula to get a different expression for the total energy of our oscillator. When we do that, what comes out is 1/2 times k times a squared. Okay. And so let's interpret that. So we could write the total energy of the oscillator as 1/2 times k times a squared. And now if I look at one of the configurations, like configuration C here, where the velocity has gone to 0, okay, then in this configuration, all the energy must be potential energy. And so we can say that when the displacement is A, the potential energy is 1/2 k times a squared. So that's sort of a derivation that tells you how to understand the potential energy in the situation where the system is displaced a certain amount from the equilibrium position. Okay, so more generally, we have this formula then. Okay, so we know now the formula for kinetic energy, we know the formula for potential energy, and then we can say that if you add those two things up at any time during the oscillation, you're going to get the same answer. You're going to get the fixed answer, which is equal to the 1/2 mv max squared, which is also equal to 1/2 k times a squared, but which more generally is just equal to the kinetic energy plus the potential energy. And so this diagram kind of indicates how the total energy is fixed during the oscillation, but it's being shared differently between potential energy and kinetic energy. At the maximum compression, it's entirely potential energy. Then as you go through the equilibrium position, it eventually is entirely kinetic energy. At the maximum extension, it's entirely potential energy, and then it keeps oscillating. Okay, so I want to do an example here that makes use of this idea of energy conservation. So what we'll find is that thinking about energy conservation is actually a very useful way to, say, predict what the maximum velocity is or what the amplitude is if you only know some other information. So maybe you only know the position and velocity at some point during the oscillation, and then you want to predict like what's going to be the maximum velocity during the oscillation. Okay, so that's basically what this question is saying. So think about that. Pause the video for a moment, and then we will discuss it. Okay, so let's have a look at this question. What it tells us is that we have a 0.5 kilogram mass. Turn this one off here. We have a 0.5 kilogram mass, and it's attached to a spring. The spring constant is 200 newtons per meter. And there we go, focusing problems. And if the spring is initially compressed by 0.1 meters, okay, so apparently it's there, 0.1 meters from the equilibrium position, what we want to know is when the mass is released, what is the speed of the block when the spring is at its equilibrium length? Okay, so that means as I release it, it'll start accelerating. We'll reach some velocity here. Because that's the equilibrium position, that will be the maximum velocity. And so what we're going to do is just use energy conservation to figure out what this is. And so in this case, we can calculate the initial energy by saying that the kinetic energy originally is equal to 0. So the energy is then just 1/2 k times delta x squared in this initial situation. And that's equal to 1/2 times 200 newtons per meter times 0.1 meters squared. And that ends up being being equal to 1 joule. Okay. So we calculate that original energy, and next we can set it equal to the energy at the final situation. So in this final situation, we're at the equilibrium position, so potential energy is 0. We've sort of defined it to be 0 at that position. And so our entire energy is equal to just 1/2 times m times v squared. And so this is E initial, E final, and then energy conservation says, so energy is conserved. And so what we can say is 1/2 m v squared in that final situation is equal to 1 joule. And so we get that V is equal to 2 times 1 joule divided by the mass, which is 0.5 kilograms. And so that ends up being 2 meters per second. So the answer is B, 2 meters per second. So that one was relatively simple because we started out in the situation with entirely potential energy and we ended up with entirely kinetic energy. But another kind of problem you might see is where I give you an initial displacement, but it's not the maximum displacement. So I could have said that the spring was initially compressed by 0.1 meter and the velocity is 0.5 meters per second to the right. And then what is the speed of the block when the spring is at its equilibrium length? So there's one like that on next week's tutorial. And the method is just the same. You calculate the initial energy, which is now the sum of a potential energy and a kinetic energy. And then you set that equal to the final energy, which in that case would just be kinetic energy. All right, well, let's go straight to another problem, also relating to energy. And it relates to two different oscillations of the same system. Okay, so this is like, here's our favorite oscillator over here. So we have a mass on a spring. So with this system, I could either displace the duck and mass by, like, say, 4 centimeters and have it oscillate. So that's kind of what's going on in the lower graph there. Or I could displace it by 8 centimeters and have it oscillate. Okay, and so those are just two different oscillations of the same system. And as you can see from the graphs, the frequency of oscillation is the same in both cases, as we expect, because the mass and the spring constant are the same, but the amplitude is clearly different. And the question is, in the second case, how does the energy compare to the first case? So think about that for a minute and choose one of these answers, and then we'll talk about it. All right, so in this situation, it's a little bit complicated just because the energy is going back and forth between kinetic and potential energy. But I think the simplest way to think about this is to use that energy is always conserved, and then to choose a particular convenient time to evaluate that energy. And so it's sort of simplest to choose one of these times when the oscillation is at a maximum, when the displacement is at a maximum. Because then what we know is that we can write the total energy, say, at that initial time, would just be 1/2 times k times the displacement squared, because the kinetic energy is equal to 0. Okay. And so in the second situation, we notice that the amplitude is 1/2 of the first amplitude. And so if we were to calculate the energy at this point, time 1, which is the total energy of, so the potential energy at time 1, which is the total energy of the first oscillation, that would be 1/2 times k times a1 squared. If you calculate the energy at time 1 for the second oscillator, then that's 1/2 times k times a2 squared. And then if you just take the ratio, E2 over E1 is going to be equal to A2 squared over A1 squared, and that ends up being 1/4. Okay. And so we could see that the oscillation with 1/2 the amplitude has an energy which is 1/4 as big as in the other case. We could have also thought about it in terms of velocity, thought about the energy here at time 1/4 of a second, or the energy here at time 1/4 of a second. And we would find that this second oscillation has a velocity which is half of the first one, because of the formula that V max is equal to A times omega. And so then we could have used the kinetic energy formula. And again, we would have found, because the V is squared in the kinetic energy formula, we would have found that the energy in the second case is 1/4 the energy in the first case. So this is a really key fact about oscillating systems. And it applies to single oscillators or even complicated systems with waves in them that we'll be talking about later on. The key fact is that the energy of an oscillation is proportional to the amplitude squared. So it's obvious that if you have a larger oscillation, that would correspond to having more energy. But this is a quantitative relationship that if you double the oscillation amplitude, you're going to double the energy. This is a really important thing to keep in mind. So you'll see this over and over again in the next 4 or 5 years during your degree. So I want to talk now about more realistic oscillators, okay, like the one that we have here, where if I started oscillating, then the actual function displacement as a function of time, it's not really a cosine, because a cosine just goes and oscillates forever. In this case, it's a pretty good approximation to a cosine, but if we were to carefully measure the displacement as a function of time over a long time, we would see that the amplitude of oscillations gradually decreases, and eventually it will stop oscillating. Why does that happen? Well, basically, what we've just understood is that that decrease in amplitude is meaning that we have less and less energy present in the oscillation. So of course, energy is conserved overall, and the fact that we see less and less energy in the oscillation must then mean that the energy is going somewhere else. And where is it going? Well, it's usually just ending up as heat. And so, for example, as this thing moves up and down through the air, it's causing the air molecules to move around. And so originally there would be some kind of airflow, and eventually that airflow would just get transformed into random motions of the air molecules. So the air around this thing would be heating up very slightly. There might also be friction in the system. At the top, maybe where the spring is connected to the stand, there could be some rubbing. And so energy could be lost to friction, which again is just heating up the materials. Or even the motion of the spring itself, the stretching and compression of the spring itself. This can cause what's called internal friction, which is again just some way of transferring the collective motion of the molecules as they stretch and compress to more random motions. And so the bottom line is, as I stretch and compress the spring, it tends to heat up a little bit, and that takes away some of our energy. So this is the kind of thing that we would expect if we actually made a plot of some oscillator versus time. Looks like our duck is actually, the amplitude is not decreasing this quickly, but in this example, we see that it decreases from 8 to 4 in about, well, 5 units of time, whatever that is. How many? 1, 2, 3, 4, 5 oscillations, and now the amplitude is half. And after another 5 oscillations, it looks like the amplitude is half. Let me just give you this to think about, related to our previous question and related to this specific graph. The question is, looking at this oscillation, what fraction of the original kinetic and potential energy remains in the oscillator at time equals 5 seconds? Okay, so hopefully you've had a chance to think about that. It's more or less just backing up this really important point that I just made. Okay, so we said that energy is proportional to amplitude squared. And so if I want to know what fraction of the original kinetic plus potential energy remains in the oscillator at t equals 5 seconds, all I have to do is look at how much has the amplitude of the oscillation decreased. And what I find is that it's gone down to 1/2 of its original amplitude. It started at x equals 8, amplitude 8. It's down to amplitude 4. And so that means that in terms of energy, we're going to have a quarter of the energy that we had originally. Looking at the extra question here, if we wait another 5 seconds, what fraction of the energy that we had at 5 seconds remains? And so what we see is that in this example, the amplitude decreases by another factor of 2 in that same amount of time. And so the energy decreases by a factor of 4 again in that same amount of time. Okay, so this is a kind of special kind of decay where we lose a certain fraction of our energy every time that a certain amount of time passes. Okay, that isn't necessarily true for every oscillator, but actually is true in a variety of examples, and it's a particularly nice system to understand mathematically. Okay, so let's try to understand for that particular kind of damped oscillation. Okay, so this is our general term for these oscillations where the frequency, where the amplitude decreases with time. That's sometimes called damping or damped oscillations. So we could try to understand for that particular kind of a damped oscillation where the amplitude decreases by the same fraction each equal period of time, we could try to find a mathematical formula for what this function looks like. So one natural period of time would be like the period. And so in this example, we see that the amplitude decreases by about a half every period. So after one period, it's a half. After another period, it's a quarter. After another period, it's an eighth of the original. Okay. So what is this mathematical function? And the standard way to describe it is to define what's called the time constant for that kind of a decay. And it's a little bit strange. So the time constant is defined to be the time after which the amplitude is decreased by a factor of 1 over e. So we just look at whatever the original amplitude is. We multiply that by 1 over e, which is 0.3679, etc. Okay, that gives us some new number. And then we look at how long do we have to wait before the amplitude is decreased to that new amplitude. Okay, so for any oscillation, we'll be able to read off that time. And that's the definition of the time constant. And so then what we can say is that after one time constant, by definition, the amplitude is A0 over E. But then after two time constants, it's going to be A0 over E squared. After three time constants, it's A0 over E cubed, and so forth. And so after n time constants, we're going to have that the amplitude is A0 over E to the n. Okay. And now n is again just the number of multiples of the time constant. And so we could say that in terms of the continuous time parameter that we're watching increase, then this n is just t divided by t0. Okay, so here t is twice t0, and so that's basically two of these time constants have gone by, and so the amplitude is A0 over E squared. Okay, and so if we take then, this is sort of a general formula for how big is the amplitude after a certain amount of time, and then we just write that n, that was the number of multiples of t0, so t over t0. So we plug that in, and then we get this formula. So what we've learned is that in the way that we defined t0, you naturally get this exponential function, an exponential decay, okay, because we, instead of putting the exponential in the denominator here, we put a minus sign in the exponent, so now it's in the numerator. So you get this exponential decay function that tells you what is your amplitude going to be after a certain amount of time. And we can check if we plug in t equals t0, we get a over e. If we plug in t equals 2t0, we get a over e squared. And so that's what we wanted. But this is a little bit nicer than this other version, because this one, we can apply that to any continuous time, regardless of whether it's a multiple of t0 or not. All right, so we're almost ready to go then. This function tells us how the amplitude of our oscillation changes with time. And so then to get the actual function for the displacement as a function of time, what we want to do is just multiply that amplitude by the oscillation function cos of omega t plus phi. Okay, so that is the final expression then. This is the mathematical representation of damped oscillations. And this was so this was assuming that we lose a certain fraction of our energy every equal period of time. So if we lose 10% of our energy in 1 second, then we lose another 10% in the next second and another 10% in the next second. Okay, so that was the assumption that went in to getting this expression. Okay, now just one final comment. There wasn't really anything special about E. The only reason E is showing up here is just in the way that we defined T0. So I could have alternatively said that T0 was the amount of time before the amplitude decreases by half. And then I would have had the same formula, but I would have 2 to the minus t over T0. Okay, so the only reason E is there is just because of the way that I define T0. But this is sort of the preferred way to write these things just from a calculus perspective, because then if you take derivatives, for example, the derivatives of exponentials are very simple. Okay, so that's more or less why we choose to write it in terms of e to the power of something rather than 2 to the power of something or 10 to the power of something. Okay, so that's all for today. We're going to start next class with an example, this example here, where you're supposed to figure out what the time constant is for some particular oscillation. And then we're going to go on to talking about what sorts of forces would actually lead to these damped oscillations. Okay, so what kind of forces do you have to put into Newton's laws in order to get this to be an actual solution of your second law of your Newton's second law equations? Okay, that's it for today. Have a good weekend.